VLSI design and verification. I think before we start discussing anything about design, first thing we can understand what the word VLSI means. I think before I start explaining anything on this word VLSI, I would like to know from you guys what you think. What is VLSI for you? When you heard this word, right, VLSI, what comes to your mind? What do you know about VLSI? Anybody? What do you think about VLSI? Please be interactive. I think it will even help me to deliver the quality session, and I think even it will help me to give so many as many information I can give. Okay? Anybody, what do you think about VLSI? Whatever you know, feel free to talk. I'm audible, right? Hello. Sure.
Yeah, you are audible.
Okay. Okay, I saw it. Okay. Let me present my view. Okay. See, generally when you refer any book or you try to do a Google on VLSI, you will just find a very simple statement first. That's a very common definition or a simple statement you will find for VLSI. What it exactly means, it just say mm, million. Now I won't say million because we are raised to several billions of transistors now. So we'll say several billions of transistors. Or I'll say billions of transistors on a single chip. It's a very simple definition you will find everywhere when you will see this word or you'll heard this word VLSI. Billions of transistors on a single chip. But actually speaking, when you heard the statement, right, the definition itself has so many internal questions inside. If you just see the statement with a different perspective and if you just try to elaborate the statement, there are so many different questions or so many different points will come out. Just to explain one of the perspective, let me take one example. Let's say uh, you just need to guess, right? I won't tell you the name. I'll just say what I have, and you will just guess and tell me what circuit it is. Okay. Suppose, or let's say I have a circuit. Okay, you're not able to see the circuit, but I'll tell you what and all components I have. I have one circuit has two XOR gate, two AND gate, and one OR gate. I have one circuit which has two XOR, two AND, and one OR gate. What do you think? Which circuit it is? Even you can type in chat box and get it from there. Whatever you guess. Okay. I, one circuit having two XOR, two AND, and one OR gate. What do you think? Which circuit it belongs
Adder circuits, no?
to? Adder, full adder particularly, right?
Yes, sir.
Okay, you say full adder, but can we really take guarantee it's a full adder? Can you take guarantee that's a full adder without looking into circuit? Are you confident enough to say it's a full adder, or do you think there is something missing, or do you think you need to still understand something to clearly say it's a full adder? Are we confident enough? It's a simple question I'm saying. Are we confident enough to say it's a full adder? You cannot say it's full header. Yes, you are very close. Maybe it's full header, but you can't guarantee. The reason the gates are not the only things who make the circuit. If you say two XOR, two AND, and one OR gate makes the full header, no, it's not correct. Until the connections are not proper, until you don't do the correct connections, it does not make the full header. So what I mean to say, these gates are not the only thing who makes the full header, but the gates and connection between them. That's what make your full header. So when we say there are several billions of transistors on a single chip, we really need to understand it's not only transistors. It's not like you have billions of transistors. You say, for example, I'll say if you talk about the generally right now, maybe whatever systems we are using, maybe you're not maybe using latest processor, but at least we are using the systems have i7 processors. And now if you go and check, there are 11.7 crore transistors on that chip. That does not mean that you just kept the transition and you get the processor, right? When it make that processor for you, when you just take that all transistor and you do a very proper connections which is required. Yes, VLSI is not limited to that. There are so many other things we do. We need to do analysis, static timing analysis, layout planning, place and route, so many other things. But the first thing you should know is it's not only about transistors. I think for me, what is proper definition? There are billions of transistors are connected to form a chip. And from this thought process, it starts. And finally, when you get your chip, it's where it ends. But in between, there are so many steps we do. Where VLSI design and verification is one part which involves into that. Now, just to understand what is exactly the design is and what are the prospective of verification when we do verification, let me first take very simple example. I think before we discuss this, we could discuss one more thing here. I think when we talk about VLSI, right, it's all belongs to chip. Now we call it chip because now everything was get too advanced and smart. It's indirectly an IC, right? Now, if you think about IC or chip, what example you have that you can take that? Do you have any real-time example you can connect and say this is very equivalent to an IC or a chip? Any example that you think it's very similar to your chip which you have in your system? See, this example is important, I think, because uh, whatever discussion we are having today is about to understand what this real estate industry in real life. And that's where you can gain your interest, right? To join the course also into the cool course also. See, for me, if you'll ask what is the best example, uh, the best example is brain. The human brain is very equivalent to an IC or a chip. The same way your brain works, the same way your chip works. Very equivalent. You know, we all know one fact that a IC or a chip can only understand binary signal. It cannot understand anything else than that. Your chip can only understand binary things. Similarly, your brain cannot understand everything. Actually, there are some neurosignals. Your brain can only understand that. Actually speaking, your brain is useless without having a complete system. Your brain cannot do anything by its own. Similarly, your chip cannot do anything by its own. It needs a system, complete system where your IC just play an important core role. Let's say you are hearing my session and I'm explaining you what this industry is. But actually speaking, your brain cannot hear. You have your ears, which act as a sensor, who well understand the audio signal. And what it do, it identify audio signal from whatever surrounding surface or surrounding area you have. And it just convert that audio signal into the signals which your brain can understand. That's the rule of your ears. Your ears are responsible to do it. Let's say if I'll give you one instructions, please move right side. Maybe all of you will move right side. But if you just try to understand, your leg cannot hear. If I'm giving you instruction, move right, it's your leg who moving right side. But actually speaking, your legs cannot hear. What exactly happens here? I said something, that signal your ear was capable to take and it converted into those signals which your brain can understand. And now your brain understood that and it's giving instruction to your leg. Directly your brain cannot also move your legs. It just do what? It just generates such size of signals which can be well understood by your legs. And that's what move your legs. And similarly, our entire chip, our system are same. It's very same. Anything you go to aerospace industry, you go consumer electronics, you go defense industry, anything you think, it's very same. And even we have to make sure that whatever chips we are making in industry, it has to be very realistic and very accurate. Let's say I'll take one example to explain one perspective. Let's say I'm I'm taking your session and we are having discussion, right? Maybe I'm very busy doing a discussion with you, and maybe my whole concentration is on what we are discussing. Let's say suddenly I'm sitting here and I'm doing discussion with you, and what happens? Suddenly I'm touching a surface which is very hot. Accidentally, I was not even aware. I was just moving my hand and thought, let's assume that I touched something which is very hot. What do you think? What I'll do next? I'll keep my hand there, or I'll immediately take it back. Anybody? What do you think? Sachin, Jaswant, Govardhan. Yeah, please feel free to talk. I think it would really help me to talk further on this.
Immediately take it back.
Yeah, immediately I'll take that. But
Yes.
actually speaking, my skin cannot understand what is hot, what is cold, right? The brain can understand. What happens if you actually understand there? It's like we have some temperature sensors on our screen. Sorry, skin. When I'm touching the surface, my skin can detect the temperature. And that temperature data it is sending to my brain. And immediately my brain is sending an instruction to take it back. You know how speedy it is? And it should be. If I have any delay getting the instruction from my brain, it will. If I'll have any delay receiving signals from my brain, obviously it will hurt my. That's the primary concern we keep. Even when we work on such chips and all, we keep three primary concerns. I won't say advantage. Actually, it's our advantage. Actually. It's our main primary advantage of VLSI industry or a chip. But for me, it's not advantage because I'm part of this industry. If you are a part of this industry, you have to make it concern because what is your concern? It becomes advantage for somebody else. If I'll put a concern, I need to have a quality session today. It will be advantage for you because you are getting a quality. Until I don't have concern, it won't become advantage for anyone. So be part of this industry, we make sure that we always get these three primary concerns: speed, area, and power. The way your brain is optimized, the brain is ready. Actually, your chip has to be make sure. And even though I was busy doing something, immediately, sorry, suddenly something came, and still I was able to take my hand back immediately. Okay, so even though I was busy doing something, even as soon as I'm touching the surface, I'm taking and my back. So you understand, try to understand. See, in between some interrupt is coming, and I was able to react immediately. That's how the processors are in the industry. Even the how the chips are in the, even though you are busy, your chip is busy doing some stuff. You have a good management inside. Maybe you say interrupt controller or anything, who's able to take care. But the problem with your brain is it need to understand when to act, when to react. It has to have some synchronization, and that synchronization pulses you are getting from your heart. Similar way we are getting clocks and all in our chip. That's a clock management system, clock generations, and that's where we get synchronized and we control each and every activity with respect to that clock. The way you control every activity with respect to your heart. So for me, the human system, human body is exactly equivalent to what we have in chips. Yes, I think we are more accurate. We have self-interpretation power, which we can not have in chip. But still, yeah, at a certain level, we are very equivalent to a chip. Now we went to when we discuss about the chip, right? It's a big flow. I think you may know it, and I think you may have idea all steps we do while we do fabrication of any chip. I won't go deeper in that, but just to explain what design and verification is, I'll take very small example. See, when we talk about design and verification, I think technically we need netlist first before we go and design anything. That's the first step we have. After getting specification and behavioral description, we work on this first step. Okay. So what you do when you start working with the specification, see, a chip. I'll just show you where exactly this come. Draw something here. See, first step when you work on chip is getting the specification. For me, actually, it's not first step. I think before that, so many inputs come, and that's when make your specification. Now, yes, it's first step, but I can say it's not the place from where you start. When you make a specification, there are so many inputs which helps you to create the specification. Like I would say, the requirement. Like when you make an IC, you first need to understand what is your requirement. It where from where the requirement come. It may come from your vendor, your customer. It may come from your previous project. It may come as a need, or it may come as the result of your R&D. There are so many things which comes and make. Let's say if I'll coming to you and say I need a mobile phone, what you knew, you need to write a specification. For example, let's say there is a simple example I'll take. Let's say someone comes to me and say, I have water tank. What I need a device from you which can keep temperature of my water tank to 75 degrees Celsius. Okay, so I need to understand first what I need to do. I understood while after doing my research and after doing analysis on this, I understand that I need a heater. I may understand I need a temperature sensor. That would help me to understand the temperature of water so that I can decide whether to turn on or turn off the heater. And this heater would help me to heat the water because I know the normal room temperature is 25 degrees Celsius. If someone say, no, I need a water tank temperature to be 10 degrees Celsius, I can understand, I know I don't need heater. I need something who can cool, who can freeze, or who can just take the temperature down. So see, that you have to do. Some specification when you write, you first get the requirement and you do some self-interpretation before you actually go and work on this. Now, I have this heater, I have this temperature sensor, but the problem is I cannot directly connect them. Even though you will directly connect them, it won't work. I want the system to work and see how exactly it's working. Now, even though you have heater, you have temperature sensor who actually works here, who actually works here, still you are not able to make your system because the brain is missing. That's the important of brain. And indirectly, what is our brain here? Chip. That's the chip what you are working with. What you will do, you will take a chip, you will connect it, you will connect heater to chip, and you will even connect temperature sensor to this chip. Now, what your chip would act as a brain here. You'll write something, you'll create a circuit, who will understand this and will control everything. It will just detect the temperature. If it's going beyond, it's going above temperature 75 degree, it will just immediately stop heater. It will just send the instructions, right? Like 1 0, and that's what control your heater. As soon as it will identify the temperature is it's below 75, it just sends the input to heater to turn on. Like VCC supply or one, it will send to your. That's how your this part would work. Just a second, huh? Just a second. Sorry for interval.
If you're talking, I cannot hear.
Okay, sorry for the disturbance. I think we can continue. Yes, the first thing you should get specification. So now, if you see, I have my devices. I know they will actually they are the actual guy who will control them, but they can't work without having a brain, and our brain is a chip. That's what we are in. That's what the industry is. Okay, so now if you see what you will do, you will take a chip, will actually make sure it's working as a brain, and it will just connect this to device and it will make sure that things are. So what I'll do, whenever this application is came to me, I'll try to understand, and I'll write a technical specification on it. I'll describe the points and I'll describe that we will need a temperature sensor. I'll need this would come as this input, and that way you will control. So the such specification would be required. There are so many inputs. I think if you, I think if we'll just discuss about specification, it'll take the whole session. But just to highlight some of the inputs, uh, the R&D results become inputs for a specification. In sometimes it become legacy. Let's say, for example, if I talk about i7 processor, right? Uh, Obviously, it's not something comes from a scratch. You already have your i5 processor. So many things you are reusing in i7, and maybe you are adding some extra feature. I would say it's your i5. You're adding some more and extra features, and it becomes i7 processor. So what happens? Your previous i5 processor specification becomes a legacy for you. Such similar to this, there are so many other points which prepare your specification. It's a first step. I think what we do, what we make sure when part of this industry, when we read specification, we make sure we read it carefully. It's a very first step, and I think it's very important for any engineers who was part of this industry. Actually, we don't even call it reading specification. We generally say it's art of reading specification. We don't. It's an art. The way you read specification is actually create a good product. Specification is the main input. It's not only for design verification. I think any engineers who work as part of this industry, they are very clear with the specification. You talk about design engineer, who will also refer the specification. You'll talk about verification guy, also refers the specification. Same specification. Not it's not like for design you have different specification, for verification you have different specification, for DFT you have different specification, for physical design you have different specification, for timing analysis you have different specification, for analog layout creation you have different specification. No, it's not same. Same specification they used to follow. Reason I'm saying this, you should understand. See, when everybody is referring this specification, how important it is to create a good technical specification with minimal bug inside. I won't say zero problem because it's not practically possible. I think certain times when you raise a bug on design, right? We used to do verification of a design. Sometimes we see the specification. Now, what is design? What is verification? Anyway, it's a plan. We will discuss this. After specification, what you do, you go into architecture. You create architecture or you write a behavioral description. It's like you create a visual effects, imaginary things, so many things inside. I think architecture is also not small thing. You need to make sure that you are selecting very particular good architectures and their descriptions for your ongoing activities, which is nothing but design and verification. Uh, just to explain one example how selective we are when we are doing our architecture. I think let me take one simple example. Uh, See, let's say there is a specification. Specification say you have four inputs. Yeah, one more thing just to clear you on specification. When I say specification, don't think it's just a words. Okay, specification content information, and it could be in any terms. It could be a block diagram, it could be a flow chart, it could be a waveform, it could be I would say a snippet of code, could be anything. See, what you do when you write specification, you make sure that you are if someone referring your specification should understand clearly what you are trying to say there. As everybody rely on that specification, it's obviously very important that you understand what the specification means. Okay, so let's say there is a simple design having simple specification, four inputs A, B, C, D, and two outputs X and Y. Okay, and specifications simply say the X is nothing but it's equals to A plus B, and your Y is nothing but it's just simply C plus D. Okay, now let's say I'll ask you this question. You have specification. Specification say this chip has four inputs and two outputs, and your X one output X is nothing but it's just addition of A and B, two inputs, and your Y is nothing but the addition of two inputs called C and D. What do you think? How many adders you need to design this? Team, what do you think? Anybody in chat box also you can type. You can talk also. I think would help. By looking into the specification, what do you think? How many adders you need here? Okay. See, if you'll see and if you'll check this out, the first impression is like you need to add. But if you really explore and if you really think on this and with your whatever expertise and experience you have, if you really go deeper, you may think you don't need to add on. You can may establish same thing into one simple adder. What idea you can bring here? You can just do alternate operations. Like first you do A plus B, then next time C plus D, A B, C D, A B C D, like alternate. Same adder you can, because it's an adder functionality, right? Why you need two adders? Same adder can be used to go and do this operation. What you will get, see, is how it will work. First of all, you will add A and B first, and then C and B, then A, B, then C. Alternatively, you will add B. That way, you will save your one adder. That's indirectly save what for you? Your area also and your power also. But yes, you need to compromise with speed. Here you get the double speed, but here you get half area. Double like half area you will work out, and even half power consumption. Now what you need to do? See, being the architecture guy also, you need to rethink on this. You should talk to your customer. You should even understand the need. You should even try to understand the targeted area of the chip. You should know where the chip is used. If it's part of consumer, I think if you are using it in your mobile phone or smartwatch or laptop, you don't struggle much with area and power. What you need higher speed always. So you can go with left side. If you are using same chip, if let's say this chip is used in somewhere in the defense industry or some aerospace industry, their power and area is the key. Especially when you work with defense, you sometimes use a device in some certain areas where power is not. Even space industry, right? We recently launched Chandrayaan to space, and there is you get the power only through a solar system or maybe through stars and all. But it's your brain which you launched that, and you have to continuously in touch with that. You are interacting to a brain edge. You have to make sure that it's always working and it's always ready for you to go and connect. If such areas where the chip is targeted, you have to make sure the area and power is very much optimized. And if you will put more logical thinkings here, see, generally, if you just ask this to me, I'll say one adder does not take much propagation delay. I think hardly would be 5 or 7 nanosecond. If one operation it can perform in 7 nanosecond, let's say 10 nanosecond. Let's say the adder is taking 10 nanosecond to do one addition. Still, in 1 second, you can do 10 raised to 8 additions. And even if you just take the worst scenarios, let's say some gaps in between and not getting the exact propagation delay or some tolerance, still I think you can do 10 raised to 7 operation in a second. How speed it is. So I think it's not bad idea to go with one adder. You can still, you don't have to speed. The humans are not that speedy. Even though you feed this adder to any system, you won't get that speed inputs. Such points we think when we make architecture. And after the architecture, we actually go into the stack where exactly you do design and you do validation. Now let me explain what is design and especially what is verification, what we do in verification, how verification actually works. Okay. See, I'll take an example. See, that's what even we look for. See, the kind of training we do, we make sure that we just don't give you knowledge. See, what if knowledge I'll give, I know it won't last for a long time. You may forget it. But if I'll give approach, I'm damn sure that it will keep forever. So that's what we try to do. Okay. So whatever we do, whatever we try always our best to give you an approach so that we can make sure that you are approach ready. Because you can't rely on whatever technology going in the market. Today I'll explain you Verilog, tomorrow system Verilog. Today I'll explain system Verilog, tomorrow some methodology. I'll explain you methodology, tomorrow UVM methodology. Today I'll explain you UVM methodology, maybe in future Python based verification. We never know where this technology would end. And if we'll just be ready with the languages, it won't help us. What exactly we do is we try to explain you what should be the approach, what should be your attitude, what should be the way of thinking, how you should think, how you should approach being a designer, what you should do, what should your approach being a verification engineer. That's what you should do. And that's what your thought process should work with. Okay, let me explain the design. Uh, See, first thing, see, as generally the flow is different, but let's assume that first step to design any chip is to get the digital circuit. Okay, the very first thing you need is digital circuit. Generally, we call it netlist, and there's a different theory. For you, just think like let's say the digital circuit. Okay. Now, when you talk about digital circuit, you do what design. Now, exactly what you do in design. For example, to get the digital circuit, let me take one example. Assume we need a digital circuit of an half meter. Let's say you are working on a chip. You want to design a chip of a half meter. Okay. The first thing you need is digital circuit. If you have digital circuit, you can proceed further and you can do other steps and you can get your chip ready. The very first, see, we are maybe exactly this is not the first step, but just to understand what design is, what verification is, we are considering this thing. Okay. So let's say you need digital circuit for half it. What do you think? How much time it will take for you to get the circuit ready? What do you think? How much time it will take for you to get the circuit ready? Think meanwhile I'll just open one more PPT help us to explain it. If I ask you to design a circuit of half a door, how much time it will take? How much time it will take? See, generally, if you do half-adder circuit design, right? It generally starts from specification. Okay, what you read specification. Let's say, assume you are doing it first time. You don't know what is half-adder. So obviously, you need to read the specification. You need to sorry. Okay, so see, when you are doing half-adder design first time, what you will do, you'll read specification. Once you read specification, you will try to decide the inputs and output. Then you will draw a truth table and then key map and equations and circuit, right? That steps you will do. And I think you are very familiar with that steps and you know how to do it. And they are very quick, right? So hardly it will take some 15 minutes for you to go and design this house. Max. But if I'll say not half header, full header, same steps you will follow, right? And not within 15 minutes, but maybe in 20 minutes or 25 minutes, you will get circuit form. Let's say after full header, if I'll ask you to design a 4-bit header, what do you think? This time, how much time will it take? First of all, if you think I'll take truth table and I'll take K map and then I'll get the equation, it may not work for you. Because this time when you talk about full adder, it's 9 inputs. 9 inputs mean you need to take a 9 variable K map, which is practically we never worked and it's very difficult to go with like instead of see K map is there to provide a conveniency uh, a very convenient solution to us so that we can easily get the circuit and even get the accurate and correct equation. But this time when we go with 9 variable, actually it becomes bulky. Instead of helping you, it actually disturbs you. So if you are thinking we'll go with KMAP, no, it won't work. Now, not KMAP, then there is no certain process that you can follow and you can get this up. Now what you will do? You need to do R&D. This 4-bit adder, which is very small, only 9. See, we started our discussion with billions of transistors, several millions of transistors, could have many, even hundreds or thousands of input. In front of thousands or hundreds of input, we are talking about a circuit which has only 9 inputs. And even a small 9 input circuit needs an R&D. Do you think, are we going on the same or correct path? No. But it was the same things we were following before 1970 actually. What we were doing or what industry was doing. And I think thanks to that engineers and people who really worked hard and get to us, which was without the help of any automation or any tools. Now 4-bit adder, a very small chip or small circuit, still we are stuck. Still we are stuck with a small circuit. What to do? What to do now? It's not possible to go and do K-map. We thought now what to do, and if you really just think, even after session, try to think. It's not it easy. Maybe if you do Google, you will get it easily. You know it's very simple circuit because you have Google. But believe me, if you start thinking by your own that I'll design it without the help of anybody, it'll take a lot of your time. Then suddenly somewhere you'll realize I'll instantiate my full header and I'll connect and I'll just instantiate 4 full header. A 4 bit header I'll take, I connect, I'll cascade them and I'll get my full header, but that's not easy. Why I'm saying all this? Because see, I just want to convey one message. If we are struggling with 4-bit adder, how we can make a chip having billions of transistors? If we are struggling with a simple circuit, how we can make a chip or circuit who process several of instructions, several of features, who contain so many functionalities. From this point, we can at least understand traditional process or traditional approach. If we will follow, it's not at all possible that we can design such level of circuit. If we cannot design such level of circuit, how we can make a chip who controls the entire system? You know, chip is everywhere now. I think I know before some time, decades or somewhere, when people was asking this question in interview, can you tell me the application of chip? People was used to think. Before they could answer the question, they used to think, oh, cheap, I think we can use it. I can see the application is laptop, the application is this, blah, 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 blah. But now the things are changed totally. Now if someone comes to you and say, can you tell me the application of chip? You don't have to think much. Just go and say where you can find the current. You can find the IC. You can find the chip. Where you can find current, you can find a chip. That's the big thing you have. You are everywhere now if you are part of this industry. You are everywhere if you are part of this industry. Any, even though you think about mechanical engineering, right? If a mechanical engineer makes a big machine, the next day it will come to you. Say, I made the machine, but I need some controlling. I need automation. The human beings can't go and control it. I need a brain. And when someone say brain, it comes to you. You know, medical industry, aerospace industry, defense industry, space industry, even automobile industry, they all rely on it. If you just see now, there are shortage of vehicles in India, shortage of four-wheelers, so many four-wheelers. There is a big shortage. If you go and ask the company why the shortage is there, they will say, no, we have cars ready, but the problem is we are missing brains. And without brains, how our car will get controlled? Our cars are not normal cars. Our cars are smart cars. Our phones are not phones, they are now smartphones. Our TVs are not only TVs, they are smart TVs now. Our air condition is not air condition, they are smart air condition. When someone says smart, I take a proud because that smart word comes through our brain, through warm I'm working. They are coming from a chip on what I am working. You know, before even medical industry was not having such things in them. If you go for a blood test, before I think I'm talking about so much behind time, but if you go for a blood report and you say it's emergency, I need my report within 15 minutes, it's very emergency, the person is in ICU. If you can't get remote immediately to me, would be a big uh, effects to our patients. Even though you have very high emergency, you need to wait for certain time before. Because lab testing where they were doing, we were what completely manual. They were taking test tubes and they were adding some drops and then shaking and waiting for some column change, and that's where they were diagnosing some disease inside. But now today the things are very changed. Why? If you now should think, now if you go for a laboratory for a blood test, you'll give your blood and say, "I'll come after half an hour." They'll say, "No, no, no, don't go. Wait 2 minutes. 5 minutes you wait. I'll give you reports. 5 minutes. Don't go. I don't want to keep this somewhere. It's very bulky to handle all such reports. Take it and you. Within 5 minutes you are getting. Even though you don't have emergency, you will get in 5 minutes. That's the big this industry is now. Because what happens now? Why it was not previously possible? Because you now got the brain who can by its own can control all the system. Even previously, when you go for such reports, they need technicians who can they were only guy who can do it. But any normal person can also go and diagnose these reports because you have the brains already available in the systems. So that's the cheapest. And see, we are targeting to be everywhere. It become, I think, for me, when you say this industry, cheap industry, VLSI industry, semiconductor industry, for me, it's like I'm the first step for everybody. Yes, you are first step. Any parts, any product which you make in world needs a chip, needs a brain, and if you need that, you need to come. Even though when you talk about AI ML, right? And some people ask me, what do you see? What is the difference between AI and ML? I'll say AI ML, whatever they do, I don't know much on deeper, or maybe what they do, I don't care right now. But I just care one thing, even they need me because they indirectly are high embedded brains, which works based on some pre-instructions or pre-things they have. I would say even they need me. Even that industry needs me because they need chips. And how from where you will get the chips? It's just a chip where you are. And because we are everywhere, we need to make sure our process is fine-tuned and very automated. If we'll just stuck like this, how we stuck in four-bit adder, it won't work. And it exactly happened to industry also during 1970s, and they really stuck. They got a very big dream that they will go through VLSI, they will go to ULSI, they will make everything. Whatever we are seeing in this world today, right? That was a dream shown by so many engineers and scientists and researchers. But they even stuck to the way we stuck, right? We are thinking how to make 4-bit data here. And we are thinking how someone can make even 8085 processor. It's a very small processor, but still have 6500 transistor count inside it. They made this during 70s in great achievements. But they literally stuck after that. They thought what to do, how to design this thing. We are stuck. And that's where the need of design came. And that's where your Verilog HDL came. That's where the VSDL came. In 1983, they found the solution and they come up with the solution for design. Now, what you do when you come to Verilog, or you come to System-log, or you come to Verilog VSDL, what you do, you just describe the behavior. You don't write the actual description of the thing, circuit. You don't even think about the circuit. You just say, I need this behavior. When you design full adder, you say, I need addition. You don't say, I need XOR gate, AND gate. You don't have to go that deeper inside. This all languages gives you a very high level of abstraction. You don't need to think about circuit. You just need to think about behavior. This language is this EDA, this kit to say what you do, you just describe the behavior. And what I'll do, I'll convert your code into a circuit. You give me your code in terms of behavior, in terms of description. Don't go deeper inside. Don't go to a lower level of abstractions. Be on higher level abstraction and just tell me what you need. What I'll do, I'll convert that code into a circuit. You write the code, and this code is not talking about the circuits. This talk is talking about the specification, the behavior you have in specification. You don't have to now worry how the circuit will form. You just need to worry about getting the code would describe the behavior. Like I'll show you something here. Like when you go to this, we generally call RTL code. When you go to that part, you'll just get the circuit. Once you have code ready, what you do is just convert your code into a circuit. You get the circuit. Now, you what you are you are able to see that you will write something, you will write a describe the behavior, and you will get the circuit right. But on other side, one big thing we are missing. While discussing this design, while discussing how we'll get the circuit, we are missing one big thing. See, let's say I took my 15 minutes and I made the design. I took my 15 minutes and I made my design. Let's half it. I took 15 minutes and made my half it. But can I really say this that my half header is proper? Am I confident that my half header would work functionally correct? No. By just following such process or by just writing the code in Verilog or VHDL or system.log, can you just come and say your code would perfectly work fine? No. What you need to do now? You need to test your circuit. If let's say it's half header circuit, you need to test it. You need to make sure you are verifying. Without doing that verification, you won't come to know whether it works perfect or not. Now, if you talk about verification or testing, the best way to verify any circuit, it's just apply all possible combination and check the respective output. It's just applying all possible combination and check the respective output. With this thought, see, this is not the thought we do have in industry. I'm just saying with this thought, let's start because that's the initial thought we come. And most of people, when I talk to them and I say what is verification, they generally say it's just apply input and check the outputs. See, this is not that industry. It's not only about driving inputs and checking out. If that is the case, why someone should run the course of 6 months? If you generally join this course where we talk about design verification, we run this course for 5 to 6 months. Why someone need, even though after having the 6 month course, we say you are just ready, but you are not become a verification. Now you need to go to industry, you need to do projects, and once you will do some projects, then only you will become a good verification engineer. Now such time periods are required. Why 6 month trainings are? Obviously, there is a lot of things available even to go and do in verification. Let me take an example so that we can by our own understand what is verification. Okay, let's start with this thought that we need to apply all possible combination and check the respective output. So like if we talk about half header, it's only two inputs. What we'll do, we'll apply these two inputs, means four combinations, 0, 0, 0, 1, 1, 0, 1, 1, and we'll check the output and we'll say, yes, our half it is right. Okay. But if you really think deeper here, no, that's a big thing. My stylus. Sorry, I missed my stylus. Okay. See, let's say, let's for example, to understand what exactly the verification means. Let's say we are verifying a circuit which has only 10 inputs. We are verifying a circuit which has only 10 inputs, only 10. Now, if you see with what thought process we have started, we need to apply 1, 0, 2, 4 inputs. Now, once you will apply this many inputs, you will actually come to know uh, are the outputs are correct and whether your circuit is working properly. Let's say what you did, just to verify this, you started with 0. You applied 0, 1, 2, 3. Like this, you reached to 99. Now, what I can say, so far you applied 100 inputs to verify this. Now, let's say after applying this 100 inputs, what you identify that out of 100 values which you applied, 95 In 95 values, your design passed. Means everything is good. But you also observed in out of 100, 5 values had some failures. Means the output was not coming correctly. What based on whatever written in specific, you were referring the specification, and as per specification, there was no outputs coming, or maybe the output was coming, but it was different than what desired. So now, what you did, you started your verification. You applied some 100 values. Out of 195 are good. 5 you don't see it's good. Now what you will do? See, first of all, you will stop. You won't continue your verification. Why? Because whatever failures you show, maybe because of it is because of there is a bug in design, or there is a bug in there is bug in whatever code you wrote. Now because of that bug, yes, you are getting that failures. Now, if we'll proceed, you'll make it multiple failures because they all are connected. Maybe one problem in design is giving all such failures. You will waste your time, and your time is valuable. Your time is very important. You should not waste it. What you will do, you will report it to design. See, you will say, hey, I started my verification and I applied some 100 values, and later I came to know 95 out of that value was good, and out of this 105 value has some problem. Now, what you will do, you will give this design back to your designer and say, what you do, I'll give you this 5 values, you apply this value and you cross check that whether the design outputs are coming correct or not. Now, first thing what designer will do, he will or she will go and check. Why? They should not even trust on you. See, even though a verification engineer say there is a problem in design on this value, you should not directly trust on that. And it really happen in industry. And it's realistic. Even though I'll see sometimes being a verification engineer, when I say I have 10 values, I have 10 bugs in design, I identified. Sometimes it really happens that it was not a bug. I mistakenly taken it, or I misunderstood it, or something. I was thinking that there is a problem in design, but it was not in design. It was somewhere in specification. It may happen. So what designer will do? It will first cross check that whether there is really a bug or not. And if let's say if will confirm yes, there is a failure, correct failures, and there is really a bug. There is a real bugs in design. What your designer will do? Designer will update the circuit. So let's say luckily whatever values we said, there is a problem in whatever values we identify. Let's say luckily we that's a bug in design, and for all such 5 values there is a problem, and designer understood it well. And what designer did, he just fixed out the things which is required, and he gave updated design. So now you have your updated design. Okay. Now you have to restart your verification, which you left earlier because you found out something, and so what for because of what you should not process. That's what you thought. Now you have to approach one. You start from 100th value. You already applied 100 value 0 to 99. You start from 101 means 100. Second approach you can take is you can just cross check this 5. Maybe designer is saying I fixed out the problem for all this 5 values you said, but you don't trust them. You just want to cross check with your point of view, and obviously you should do it. And then you want to continue with 100. Third choice you have, you should the third choice, sorry, you can have is you can start from scratch. What do you think? What I should do? I should go with first, I should go with second, or I should start from scratch? What I should do? Most of you maybe think second approach. First, I don't think anyone would think. You will go with second. And yes, the second approach is good because you should cross check, and it really happens. Believe me, in real time project also, when we verify, uh, we re-verify the design which is updated because of the previous bug, we actually see the bugs are not resolved properly, and we really had discussion with designer, and sometimes we again find some real issues. So even the designer should always cross check what verification engineers has reported. Even the verification engineer should always cross check what designer has updated in the design. So this is good. But what is the surety that other 95 values which was passing earlier does not has any side effect? Obviously, when designer is updating something in the code or something in the design, there are chance that it creates the side effect. Now, because there is a risk of side effect, we need to also make sure this 95 are still passing. So now you will do what? You won't go with the second, you will go with scratch. Means every time when design get updated, you need to start from scratch. So if you think just I'll apply value, I'll get the output and I'll see. This is the actual one of the real problem. No, there are so many things we do. I'm not saying only this, but this is one of the thing you should consider while doing verification. Now what happens? You started doing this verification, you reached to 1022, everything was good, design was passing, you were happy. But at last value, which was 1023, you applied, and suddenly you observe something. There was a problem in output. There was a problem in design. A bug reported. I think you were in more tension than designer because you need to again start from zero. You already reached to last, and you have to start from zero. Let's say what happens in morning. The team had one meeting. They did a meeting. They thought we are missing one signal enable in our design. We should add it. So now this 10 becomes 11. In meeting, they took one decision that we should have enable. So we are missing enable signal in our design. Everyone agreed. Designer added one more signal in design that was enable, and your design has now 11 signals. Now, designer will do what? He'll just add something and he'll get the design ready. But verification engineer, what it will? The combinations are increased from 1024 to 2048, double. Every single input when you increase in design, double the. So let's say there was a design in which has 8 bit inputs. There was a data input which was of 8 bit. Later, they when they were doing discussion with customer said that 8 bit input won't work out. I think data input should be of 16. Now you already reached to a certain level in project, and now the decision came that the data bit should be of 16 bit. Verification engineer would be completely survive. Why? 2 raised to 8 is 256. 2 raised to 16 is 65,536. Every input when you add, it doubles your, not double, it increase your efforts in power of 2. Some would say I'm just adding 2 more inputs, or I'm just adding 2 more bits here. You will say no, because your efforts is increased by 2 raised to 2 means 4. So if you really see what conclusion we are getting from here, if we are practically thinking that it's just about applying all possible inputs and checking output, no, it's not practically possible. Then what application engineer to do? It should come with different approach. What approach? Let me explain. I'll take one example to explain what kind of approach you should be. Yeah, please interrupt me for any doubts or query you have in between. Okay. So, okay, one thing we are clear now. If you are thinking that it's just about applying whatever possible values we have and checking the outputs, no, practically it's not possible. Even see, what kind of chips you are working today. Applying all possible combinations single time without any bug. You think design is good, there is no bug. Single also will apply, it takes years. and even you don't have enough. See, your company won't even give you enough time to apply a single time. If you just think I'll apply all combination or whatever it's there one time, that time also you don't. Then what you will exactly do? So very first thing, I'll take one example. For example, you are working on one design having 8 inputs. And there is one input, one output. Okay. So if I see 8 inputs, I think I have 256 combinations. If I'll just think about combination, but as we know, we should not apply that. Then what we should do? Let's say that the circuit is like this. The output is Y and input is this A and B and C and D and E and F, C, 8 inputs. Okay. Generally, you won't see code. I think the verification engineer should never see the design code. Uh, when you say design has problem, what is your reference point specification? So you refer specification, the same specification what designer is referring, and based on that you say whether the verification is passed on. So you won't see code actually. Just to explain, I'm just writing the code. Yeah. So now let's say you want to verify this. Okay. You want to verify this. The one way is to apply all possible combinations. Other way, what is other way? Now, first way is practically not possible. Then what we should do? What kind of thought process we have? What kind of approach we should have while doing this? So let me take one side example here to explain this actually. A small example which I think understandable for all. Let's say you are verifying a mobile, a chip of who belongs to mobile. Okay. If you see there are three highlighted feature. One is call, let's say an SMS and music play. Okay. Now your responsibility is to go and verify this call as an music player features. What you'll do? First, you will take, let's say, take call. What you will do? You will read specification. You will read specification carefully. You will try to understand what this feature says, what and all are inputs of call, what and all are the outputs of call, what is the exact functionality for it. That's the attitude, and that's the real attitude you should even carry when you are working with verification industry. So what you will do, you'll carefully read the call specification, try to understand the exact functionality, the features, what involved in call, any sub features, what are the inputs, what are the outputs. So what you will do, you'll try to understand that, and let's say you understood what is call, you well understood what is inputs of call, what are the outputs of call. So what you will do, you'll apply all inputs required for call, and you will check the output. So what you are doing, whatever inputs are required to verify call, you are doing it, and you are verifying that whether this is working properly or not. And what you observe, everything was good. Maybe you'll put a tick mark on call and say, yes, I have verified the call feature. Later, you will take the next feature. Maybe your next feature is SMS. What you will do, you will read again, same way, you will read functionality. You will try to find out the inputs possible. You will apply these inputs and you will check the outputs of SMS. And if everything is good, you will put tick. Same way you will do basically. Now, what you did, you actually applied you did whatever you are required to do for call SMS and music players. But once you will complete this, you will may realize one point. If I'll ask you what you think is missing here, anyone, am I missing anything in my verification, or do you think anything I can add? CB, what if I'm talking on call and same time I'm getting message? What if I'm hearing music on music player the same time I'm receiving the call? Obviously, it should work. If someone missed this feature, let's say while talking on call, you are not getting message. You are not verified it. You missed it. You know your verification is very, 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 very much important. Verification engineers are putting signs. So when someone say is this chip is okay, you put sign yes okay. You are the one who sign. You are your sign values. You give signature inside below that. Yeah, I verified and I see there is no problem. If anything problematic come in future, it's you are the responsible. The one who make it, they are not responsible. Designer who works on this and builds the design, they are not responsible. You are actually responsible because you took the credit saying that this chip is working fine and I'm taking full credit that I have verified it very properly. So it's your responsibility. Now, if let's say you launch your phone in the market with having this bug in the phone, you are not able to get message, SMS while talking on call. It's a big bug. You won't be able to sell your even initially you will sell your some of the pieces. Later you will see your market is not. No one is ready to buy your phone because if they are not getting message at the time they are talking on call, they don't want to buy it because they will meet very important messages during that time. And that can harm their career, that can harm their even bank balance, they can harm their securities. So many things can damage you. Right? Let's say someone want to just hack my account during like let's say someone want to hack my account. What they will do, they will call me because if they are talking on me on call, I won't be able to get the message which is which is it's to indicate me that there is some suspicious activity. I'm talking on call. I'm searching job, but I'm talk on call with some friends. Later, in between, someone is messaging me for interview. I'm not able to get that message. That will damage my career also. No one is ready to buy this phone. See how much attractive your mobile phone is, how much economic it is, how much good feature it have inside. It still does not matter if you have this bug inside. So this small thing which you think very small can be a very critical part. So now, if you observe or if you just understand, while doing such or while thinking about this verification process, what I did, I actually not thought about values. I more thought about functionalities. And that's what we do being a part of this verification engine. We never think about values. Being a verification engineer, we more think about functionality and feature. We just think I need to verify this functionality and what and all functionalities I need to verify when we work on this. When I'll deeply work on call and message functionality, I'll come to know, yeah, there should be one functionality. The SMS should properly work when the call is initiated. We never think about values, we more think about function. Now, based on that thinking, if I'll verify this, I should just try to understand. See, if I'll just deeply go inside that, right, I'll get two statements. One, if any value is zero, if any input is zero, the output will zero. Second point I'll get, if all inputs are one, the output will become one. This is functionality. I should not look into the code. Even I should not look into the 8 inputs. Forget about inputs. Values. Just try to focus on functionality. What the functionality say? If any of your input is zero, your output should be zero. If all the inputs are one, your output should be one. Now, based on that, what you will do? You will think, okay, any of input zero, let me verify this functionality. Let me make this input zero and see whether output is zero or not. But while doing that stuff, you should make sure other inputs are one. Else, how will take credit? When you make your A zero, you are waiting for your output to zero because of A, not because of B, not because of C, not because of D. You are looking for output to be zero because of A. Because any input, that's the functionality. You just caught this word, any input. Any means any input. You take C, you take A individually, and they are capable enough to make your output zero. So what you will do, you will make your A zero. Other inputs you will compulsory make one because when you are getting output zero, you are very confident that because of A, not because. Now, one input, second input, you should check each and every input because they are equivalent contribution in the output. What if let's say someone missed D, writing D here? You won't be able to capture if we are not applying all inputs which is required. So what you will do next input, you will target B. Similarly, you will target C. Similarly, you will target D. Now here you will capture that D is missing because you won't get output 0, you will get output 1. That way you will apply 8 inputs and one more input where you will make all inputs 1 because you want to make sure second functionality is also verified. To verify this functionality, you need this value. To verify this functionality, you need 8 inputs, where one bit is 0, other bits are 1. How much inputs you thought so far? 9. See, where is your 256 and where is 9? And this 9 input, you are so confident. You can definitely say you don't have to apply 256. By just applying this 9 inputs, you can take credit of all 256. Just see this 9 input that has that confidence. It will make sure that your design is bug free without applying 256 inputs. See, these inputs are so valuable. Even though you will apply 255 out of 256, if you are applying 255 values, but if you are missing one value which is out of this value, your verification is not complete. You apply 250, you apply 256, 250 combination. If you miss any value from this 9 values, your verification is not complete. And just this 9 values, your verification is complete. And that's how we approach, that's how we work. See, it's more important than your Verilog, system log, and UV. They call it planning test cases. We plan test cases. We don't get diverted because of value. We totally focus on functionality. I got two functionality here. One functionality I verify with one input. Second functionality I verified with 8 inputs. That's it. That's what I'll do while doing verification of this. Similarly, you say marks, you say any specification, you'll bring it to me. I'll just focus on functionality. I'll just say what I need to completely verify this functionality. And that's what my point of focus would be. This is one point. So we got our one point as, if I say one point, sorry, just note it down here. Yeah, one point, planning. And that's very important. Planning of and verification strategy. Because when you plan test cases, you should also know what should be your output. You should have expectations. Something. Now, second thing, what we do when we do verification. It's very simple. I think it's depend on your common sense and self. And for me, I think when someone say verification industry, I totally believe it that it's more rely on human being common sense and self interpretations. I think with your good communication, common sense, and with your self interpretation, you can easily understand what verification industry is doing. I'll take you one example here. This example is a very good example to understand what we do. And it's not depend on experience or not depend on something. It depends on completely on your approach, the way you think. And that's what I'm saying. We try to change that in training. We try to get that thoughts. We try that you get that thoughts and approach while doing this training so that you can contribute from first day in the industry when you do this training. Let me take the second thing. Let's say I have one code. Don't worry. We are not discussing any code here. It's just a small example which everybody can understand. Let's say I have small code. I'll explain what this code is. Right side don't focus, it's just statement 1, 2, 3. We don't have to worry about what exactly we are writing here. Let me explain what it exactly it is. The select is of 5 bit. So obviously there is 32 possibilities. So now for different possibilities, we wrote something. Like say if the value of select is out of 1, 5, 10, 14, 19, 21, statement 1 will exist. If the value of select is the out of this 0, 4, 7, 11, 16, 24, 30, statement 2 will. Similarly for other values, the statements will. Now let's say we gave verification of this code to 1. We select 2 person to verify the same code. So what we did, we selected 2 engineers who will work on this. One was, let's say the name of one guy is, so let's say one is X, one guy name is X. So we gave responsibility of verifying this code to one guy called X and another guy is Y. Now the problem was they didn't had enough time. We provided the time to them, and we asked that you should verify this code in this much time only. You don't have enough time, or else they can may apply the both the possibility. Or let's take it different way. I think let's say we gave this code to verify to 2 person named X and Y. We totally make them free. We made them free that whatever they want to do they can do. Obviously they were smart and they were knowing one thing, that applying all possible combination is not a good idea. So maybe I don't know what X thought, but X come up with some value. I think when I show the verification was over for X, I show X has applied this many values. Let's say we went with the X has applied this many. So when you see the verification of X, it has this many values as part of his stimulus. X has this many value as part of his stimulus. And when same thing we gave it to Y, Y just came up with this many value. See the code and just let me know what do you think. Whose verification is good? Is it of X or of Y? What do you think? Whose verification is better? X or Y? Just observe. You have code, you have values. Take your 2 minutes and observe. What do you think? Whose verification is better? If you really go deeper inside, first impression you will get X is better because what you see, values applied by X is more than Y. But actually speaking, when you will closely observe, Y is better. Why? Because see, if you see X is covering these 3 statements, it's not covering any value from this. But the same side, if you see or if you observe your, it's covering 4 statements. Even though X has multiple values, more values, or maybe it's more than cross 2 of Y, still the verification of Y is better. What conclusion we are getting here? It's not about verification, is not about applying maximum values. It's not about giving all possibles. It's about verifying the functionality. It's about covering the more part of the. And this particular thing you call code coverage. That's one of the perspective we cover. So second thing, we make sure that we had good code coverage. And it's very easy, right? You can also understand why is better. And if I'll ask how much coverage you will get for 75, you'll say 7. Sorry, how much coverage you will get for X, you will say 75%, because it's only covering 3 statements. And if I'll ask how to make a code average of X 100%, most of you will say add one value from the statement. You will add 4, 7, whatever. You'll make your code coverage 100% for X. So everything is very, very easy to understand, and it's like, as I said, it's just depend on your own common sense. You know the importance of coverage by your own. You know how to even calculate the percentage. You even know how to improve the coverage. This is one of the perspective we try to achieve in verification. Sorry, I think. Okay, so third important thing we do is function coverage. Now, I think without constant under verification, I can't explain this, but I'll try to explain with one more perspective. See, generally, what happens when we talk about code coverage, you are actually verifying that whether the code what you wrote, you are executing the whole code or not. Each and every line of the code is exercised or not. So that if you miss anything, you'll figure out. Let's say by mistake, instead of statement 2, someone wrote statement 1. Now, even though applying after applying this many values, X won't be able to find out this bug. The reason applying so many values is also not that important. Why is having good verification? Because why is able to find out this bug. So what your code coverage do? It just make sure that each and every line of your code is exercised. But the problem is what we do, we read the specification, and generally after reading the specification, we write the code. Now what you are doing, you are reading your specification line by line, and you are implementing the design code. What's the guarantee that what and all features are given in specification? And remember one point, specification is not like every features would be given by number, one feature, second feature, third. No, you have to even identify the features, and you have to implement. Like someone say, I want to implement the mobile phone chip where call and message is there. You need to identify that there is a possibility that if you are talking on call, you can get message. If let's say someone is coming to you saying, I need vending machine, which takes two types of coin, 1 rupees coin, 2 rupees coin, and the product price is 3. So now you can get 1 rupees coin, 2 rupees coin, and when the total sum is 3, you will get the product. Now, if someone can also deposit 2 rupees coin, in that case you have 4 rupees. Now, what to do with that 1 rupees? Such kind of thinking you should produce while reading the specification itself. So now the designer would read the specification, would try to identify the different functionalities and features inside, and will implement the code. Now, what is the guarantee that it will implement each and every feature, each and every functionality written in the specification? Let's say there was 100 features, and what designer did, designer has implemented only 96 features, or designer has missed out. Now, what is the guarantee, or what is the the proof that each and every functionalities and features are implemented? It may happen that you have only implemented 96 and you have missed out 4. Your code coverage cannot go and show you that, because code coverage and only tells you about what code is implemented. Code coverage will say, yeah, you implemented 96 feature and all 96 features are accessible. But what about the 4 missing features? So functional coverage is one of the point perspective where we do what? We try to write some coverage on the specification we read, and we try to identify each and every feature which we have inside, so that if any feature or functionality we missed while implementing the design, we can identify. That's one of the segment we have when we do we do verification. See, similarly, we have checkers. Similarly, we have, I'll say, assertions. I think these all are many perspective we have. For that, you have to little understand verification. I think then only you will be able to understand what they are. I think if we have more discussion in future, we can even discuss what and all these checkers are and why we need checkers. Because still one problem is not solved. See, I told you, you need multiple iterations. And as soon as you see problem in design, you have to restart from where you start. Let's say even though you thought 1,000 features, Even though there was hundreds of possibility in your project, what you did, you smartly thought and you come up with your test plan. And in your test case, now we are only applying 100. See what we did in just now with one of the case we discussed. We had 256 combination and we just applied 9. Similarly, let's say what you did hard work, and out of 10,000 possibility in your project, you thought 100. You did very good job. Now only you have 100 values to apply instead of 10,000. But still think, whenever you will see design problem, you have to reapply all 100. Still you are in the same phase. That problem is not solved. Even though you will have Verilog, you have to rerun the simulation. You need to re-observe the outputs, and you in checking running the simulation and checking the outputs is not that easy, and it's not that fast. Takes its own time. One test case when we generally run in a project, a small average project I'm talking, it takes 10 to 15 minutes minimum. Even I am working as right now I'm working in one of the project. I'm one of the project where it takes 4 hours for one test case to submit, and after that it takes 15 to half an hour for me to observe the waveform and see what outputs are coming and confirm that whether the outputs are correct or not. Every time in design has a problem. If I'll just repeat the same approach, practically I won't be able to complete my project. For the same reason, we need checkers who are the smart. Like if I'll just say 2 lines on checkers, they predict the outputs. Like how designer write the code and generate the output, verification engineer also write the code. They also write this not the similar code. What they do, designer read the same specification, verification engineer also read. They both, because they both read the same specification, whatever code they write has same behavior. Code is not same, but behavior is same. And because behavior is same, what output verification engineer is getting, which we call expected output. So what verification engineer do? It writes some code who mimic the behavior, not mimic the design code. It mimics the behavior of specification, and based on that, it gets the expected output. And what you do, you match this expected output to the actual output you are getting from design. If you don't, if it is not matching, you throw an error, and that's where your verification becomes completely automatic. To whom we call self-checking verification, and that's where you need more efforts because now you need to be like designer. Yes, the perspective is very different. The designer is having different perspective. The designer has to design something which converts into hardware, whereas the verification engineer is free. They don't need to worry about whether my code would be able to convert into hardware or not. But at least they need to make sure the behavior is same, which is written in specification. So we write some kind of checker logic through what we make the verification automated, and that's where we make sure that every time when the design is updated, we don't do anything. We run the script. It makes sure that it runs all the checkers, and it just check the outputs. If outputs has mismatch, it just alert us. So it saves lot of our efforts. Now we only spend the time to debug the failures. We don't spend our time to see whether the test is passing on. It is something automated, but it's not automatic by its own. It us who made it automated. We need to think. We need to write the logic, and it really take our good efforts and good time to go into it. So it's not like only values and outputs. You need to make sure that you have good test planning. You need to make sure you are able to cover whole of your code. You need to make sure all your functionality and features are implemented. You need to make sure your verification is self-checked, else practically you won't be able to finish your project for verification. So these are all the perspective which we think we should cover, and that's what we do in verification. Okay, I think verification itself is a big thing. If I'll just talk about that, it takes a week for me to go and discuss that. But I tried my best to explain what verification means to me within whatever timeline I have possible for you to go and give. I hope everybody understood and enjoyed the session. Maybe now you can ask any query or any question you have. Siva, you are here?
Yeah, I'm there. I'm there.
Yeah, I think we are good. We can.
Okay, yeah. Thanks. Monica, any questions? Sachin, Yashwant, any questions you guys can ask?
Sir, it is similar to IT field like software testing.
No, I think you do programming same way the software engineers do, but your end target is hardware, which differentiate. Because when you talk about software, the simulation goes sequential. Like if you see your code, right, it starts from first line. In software industry, when you think about simulation, it starts from first line and end at the last line. It goes sequential. But in it's not sequential, or I can't say even parallel. It's mixed hybrid approach. One main thing you don't see in software is simulation time. We have something called simulation time, and we whatever we are writing it converts into an actual hardware, and whatever we are verifying it's an actual hardware. So there is more foundations and more logical thinking is required compared to what we do in software. Yeah, but yes, certain level, you both guys are doing programming, and even you are spending your time doing debugging, doing analytical thinkings, doing thinking logics. That they're where you are safe. But other perspective, they are totally different than what you do in software.
Okay.
But you involve programming when you do design verification. Yes, it's completely on software.
Yes.
And even this Verilog SV is C-based languages. If you talk about SV, it has C data types, it has C++ OOPs, even it has some other features from different languages. So C and C++ is mother of all such languages. So you will may find similarity. Yes.
Which is the tool we use for training
Hmm?
purpose?
Tool.
Which is the tool we are using here?
Okay, yeah, tool. Tool. Initially, when we start design, we use Xiling Vivado to understand what is FPGA and what is synthesizable RTLs and all. Initial days. But once we are good, we start with Questas, Siemens product. So you actually get your hands on with the industrial tool. In verification industry, just have three tools from three different companies. One is from Cadence, one is from Synopsys, and one is from uh, Siemens, which was Mentor Graphics before. And Mentor Graphics in QuastaSim is one of the most used tool in verification. And with
This
respect to
Cadence
resource,
people use NC launch, right?
what?
Cadence use NC launch, right?
Yeah, yes, yes. See, when if I talk about tool, right? Once you get the approach, see, you need to understand how to use tool. Now, once you understand one tool,
Okay.
you are able to use any other tool because it's like mobile phone. You understood one mobile phone, you know what and all features are there and how we
Correct.
operate it. You can operate any phones in the world, right? So same way the tool are. One tool you use, properly focus on the features and the way you should use the tool, and you are good to go with other tools. And if you want to talk about resources, right, verification resources, generally why the demand of verification engineer is very high in the market because see, whenever you see a chip, if they hire one design engineer, with that they may hire three or four verification. It even true with my current project. I think the project I am working has one design engineer in Canada. He sits in Canada, only one person who do design. I think later when they struggled with some features, they added one support engineer. So only two engineers still I'll say. Whereas in Bangalore, we are a team of 12 people who do verification of the same project. See how big the scope is here. 70% of your cost or 70% of resources you spend behind doing verification. And that's where the demands come increased and you get sooner jobs and you get good mark. Even though when the market has recession, you still see jobs for you because the demands are more compared to any other engineers.
That's true, actually. That's what
Sir, what is the difference between this one, sir, DFT and DV? Design for
See,
test and design.
DV, yeah, I'll tell you, DV is completely different here. See, when you talk about DV, DV is on software. So when you design RTL, right? RTL, after RTL, you create the circuit, which is indirectly netlist. Okay. But DFT is done once your fabrication is over. Once you have your chip in your hand, you do actually DFT, design for testability. where you make sure that your chip is working functionally as expected. So for that you create the hardware system for complete board, and you try to give inputs on the hardware level and you verify the outputs. So it's completely different. And what you are doing in DV, you can't do it DFT, because let's say you are verifying 100 inputs in DV. I think hardly you can verify 5 or 10 inputs at DFT. DFT is done for each and every chip. See, when I talk about DFT, if you, let's say you are making a chip, 100 chip for one particular product. 100 chips for like 100 products you are targeting market. If you have 100 chips, each and every chip has to go through a DFT process. Individually, you do testing of each. It's like testing. You do it for each and individual chips. When you talk about DV, you don't do it for chip, any chip, particular chip. You do it for specification. You do it for the RTL you wrote, which will convert into a chips. Not chip, I'll say chips, multiple chips. So DV is for only functionality or a particular RTL, whereas DFT for each and every chip, where you taste some of the inputs, standard inputs which you think you should taste. You taste the chips under some temperature controls. You think you see that whether your chip is working good with some conditions which you thought should work. Even you vary them. You try to inject some noise, and even you try to vary some voltage and make sure it works good with all the perspective, which does not come for DB, like temperature, voltage varyings, and all. Does not come because it's all on software level.
Okay.
Sir, in the course, will we be working only on the software tools or hardware also will be involved, sir?
No, see, generally I had 10 year of experience. I have decade of experience of this industry. I never seen hardware of any of a project I got. So because it's very end process, it comes very late, and uh, we may see images, but we just generally don't involve into hardware. Yeah, but for you to understand how FPGA, like how hardware looks like, and how we dump the code and how we connect the different parts of the project to one device, yes, we would have some sessions where we'll show you hardware, and we'll show how we write the code in Verilog, how we convert that code into a bit file, how we dump that code into an FPGA board, how we connect all external system to a FPGA board, and how we execute that. So we would have separate sessions. But actually speaking, when you go to industry, that's some that knowledge does not, actually it's good to have, but it's not compulsory. But just to explore that part also, we would have some session on that.
Okay, sir. Thank you.
Yeah, okay. Siva, I think we are good.
Yeah, thank you. Thanks for your time.
Yeah. Thank you. Thanks all.
Bye.
Thank you.